So this is a new talk. I've never given this anywhere. It's called Blazin Fast PromQL. And the story behind the title is a very long time ago. This is 12 years ago, I think. I stood up at South by Southwest in Austin and gave a talk about blazing fast Cassandra with a chap from Twitter. And that was like my big break as like a public speaker, if you like. So I thought I'd reuse the title. That's it, really. I've got notes on my phone, so if you see me looking down here, that's what I'm doing. So I'm not here to talk about, no, that's back. I'm not here to talk about Cortex, but I'm here to talk about a very small bit of Cortex. So, but to give you the context, Cortex is this project I've been working on for 3 years to build a horizontally scalable, clustered version of Prometheus. And I've given a talk at the Prometheus meetup and at various conferences about it. Cortex is really just like a clustered version of Prometheus. It uses the same PromQL engine, which is going to be the rest of the talk. It uses the same chunk format. And so like a lot of the code base is the same, and all we've really done is glue it together differently and used a whole bunch of like distributed systems algorithms and consistent hashing and so on to make it horizontally scalable. Cortex gives you, a global view. You're very familiar, like this is basically the same problem that Thanos is solving. It gives you no gaps in your charts, it gives you durable long-term storage, and it's multi-tenant. So it's very similar in its problem statement to Thanos. Solves it in a completely different way, and that's kind of cool, I think, like having two completely different solutions to the same problem. But anyway, not here to talk about that. Part of this global view problem is, in the Prometheus world, we say, cardinality shouldn't be too large. And what we really mean by that is, in a single Prometheus server and in a single query, you really don't want to consider more than about 100,000 different time series. So when you're doing one of these big aggregations, try not to aggregate together more than 100,000 time series. That's the rule of thumb we say. Because if you do, it'll be slow and you might break the server. But when you start to say to people, with something like Cortex or with something like Thanos, you can send all of your metrics into one Cortex cluster, or with Thanos Query, you can query all of your metrics for multiple different Prometheus servers, then suddenly this rule of 100,000 time series becomes a lot harder to stick to. I should stand in front of the camera, sorry. Hello. So it's quite easy if you've got 10 Prometheus servers. We, at Grafana Labs, I think we've got about 15 Kubernetes clusters spread all around the world. And so we've got a bunch of Prometheus servers, 15 I imagine. And so it's really easy in a query to touch like 1 million series if you're doing one of these series that touches metrics from every cluster. And this kind of breaks that cardinality limit that we've talked about, and it makes these queries slow. So to give you an example, I didn't do the maths, but somewhere else I've done the maths. Like it's very easy to write a query that will touch a couple of 100 gigabytes of data. And you expect that query to return quickly. And so this is hard, and that's what the rest of this talk is about. So this is what we started with. This is very similar. It looks a lot like the Thanos query. If you replace this bit with Thanos and this bit with the sidecar, then this is just the Thanos query. We call it the query or the Cortex query. We call these things the same. And we'd use the same PromQL engine as Thanos and as Prometheus does. And we started off in a very similar way. So you can have more than one of these. They're stateless. You can run as many as you like. And if you notice queries are slow, you run more. Now the problem with that is that doesn't actually help. When queries are slow, it's very rare to see a high concurrent query load. Most people load a dashboard, it reloads its graphs every 5 seconds if you're a real maniac, and it so you're seeing maybe 4 or 5 panels. You're seeing 1 QPS from that dashboard. That's not a high query load. I don't need multiple parallel queries to make that fast. And what's more, like adding more queries is not really going to make it fast. So this was where we were just over a year ago. My phone keeps locking, so yeah, like when you send me one big query that's looking back over 30 days of data, that's just going to hit a single query. And even worse, it's actually going to hit a single Go routine and a single query that's going to sit there and load all the data in, process its way through it, and send you the result. And effectively, the longer you make the query, the slower it's going to get. And you're bound here by the speed of the silicon you're running on. And I don't know whether you know, but chips are getting slower. They're not getting faster. They're getting more cores. So we can run more of these in parallel, but that doesn't help me because I don't have a high concurrent load. I have a low concurrent load, but people are sending me queries for 30 days or more. So this is kind of giving you a clue as to what we're going to do. But first, before we talk about that, so first thing we did is we had caching. We had caching down here. And I believe Thanos has something similar as well. So we actually just use memcaches. This was a tricky one. This was done by Gotham, one of the other Prometheus maintainers. This is super interesting because you get this bit wrong, there's gaps in your graphs. And that, as you remember, slide 1 is kind of what we're trying to avoid. So making sure that your index cache is both effective, but also doesn't over-cache and occasionally return stale results. That was really tricky. I could give a whole 20-minute talk just about that, but it's a bit more dry than this one, so I'll avoid it. Luckily, the chunk cache down here, chunks are immutable. So once we've written them, we can cache them forever. They're never going to change. Even better, they're actually content addressed. So if you have identical chunks, they dedupe themselves. It's lovely. But that didn't really help. It made it faster. So what we did is we stuck this thing in front, and we called it, because it's in front of the querier, we called it the query frontend. Yeah, naming scheme. Does what this says on the tin. Guess what the ingesters do? And what we did, the whole inspiration for the query frontend was taken from this service, this piece of code written by Comcast called Trickster. Who here knows about Trickster? Who here uses Trickster? I was expecting a lot more. I was expecting someone to say yes. Who put their hand up for knowing about it? No, I'm not going to ask. I'm going to ask you. Why don't you use it if you know about it? You don't have to scale. Okay, fair enough. Good answer. Go on then.
We heard some stories about queries against Thanos, where incomplete results can be cached.
Oh, okay. I'm not going to spread FUD, so I'm not going to repeat that for the stream. Which people are going to be way more interested to what the answer was now. No, I mean, it's fine. It works. It does what it says. But we set out to build our own one because, nothing's done properly unless you've done it personally yourself. No, we wanted to do things slightly differently. We actually originally looked at just embedding Trickster into Cortex. One of the biggest problems I found with Trickster, and this is not a dig, it's actually something they're fixing right now, is that it was quite hard to embed, and they're actually trying to fix that. So, this isn't a dig at Trickster, this is, I really like their idea, so much that I wanted to write my own version. And we wanted to, again, we've got an addiction to memcache, so we wanted to store the results in memcache. And I could talk about why we like memcache. We don't like in-process caches because we like to upgrade our software very, very regularly. And so we don't like persistent caches on disk because disks are slow and so are SSDs. So we like memcache because it's fast and it's separate to our processes. So we can upgrade these and our memcaches can last for days, weeks, months before we have to upgrade them. So we added caching everywhere. And the rest of this talk, so far this has been the introduction. Sorry. This talk is really about this one component. How did we add caching to Cortex? So I've now zoomed in to the query front end. You get a request in, and this is a PromQL request we'll all be now intimately familiar with. And in fact, it's very similar to the metric you were using. And so we're looking for the shipping job. We're looking for the rate of requests to the shipping job. And I'm going to tell you this is over 5 days, 4 days or something. First thing we do is we align the edges of this request to its step. And this is something which people will tell you is a bad idea and you shouldn't do, because we don't actually execute the query you gave us. We execute a slightly different query. But we hope you don't notice. And you can turn it off, it's optional. But it's kind of important. The other thing we do, because we align this edge, the other thing we do is we now actually in Grafana by default, so one of the benefits of working for Grafana Labs is this is, the bit in front isn't just a black box anymore. I can influence how it does its queries. And so we now just do this in the front end. So we now honor the query you send us because the query you send us is correctly aligned, which it should have been to begin with. Anyway, so the reason we do this is because if you ask a query at now, aligned to 15 seconds, what happens is Prometheus goes back from now, goes back 15 seconds, executes an instant query, goes back 15 seconds, executes an instant query, so on. You can imagine, right? If you ask a query now, so 4 or 5 seconds later, it goes back 15 seconds, it goes back. And you can see they don't align. So you're going to get a subtly and slightly different result. And this is why in early versions of Grafana, if you mash the refresh, the lines jumped about a bit, right, which sucks, right? So we align them so that if you ask a query now, we actually go back to the last 15-second boundary. And if you ask a query now, we'll go back to, and then once you get to the next 15 seconds, you get that. And so this aligning is important because it increases the cacheability of the result. If we didn't have this, we couldn't actually cache results with any kind of accuracy. So then the next thing we do, and this is magic, we split the query up by day. This is cool. I like this. This is the whole reason it exists, to be honest. Caching is there. This means, the key thing here, right, is these queries are now executed independently. And so they're executed on multiple cores, on multiple different Go routines. So now we can scale with my multi-core processor. So you ask me a 30-day query, I go and issue 31-day queries, and I execute them in parallel. And now that problem I was talking about where scaling up, it's not finished, there's another reveal. Scaling up my number of queries gives me more query performance, lowers my query latency. And this is a general, like if anyone studied queuing theory, this is trading latency and throughput. Right, this is all I'm doing. I didn't invent this. And then we do the second thing. We go and look up in the cache, and we find out, actually I've asked for this day before, so I don't need to answer it, and I've asked for this day before, so I don't need to ask Prometheus for that. But I haven't seen this day in the cache. Maybe it got evicted, maybe the cache forgot about it, it's memcache. And what you'll also notice is, I've only seen a bit of this day, I haven't seen the whole thing, so I have to go and kind of stitch the query together. And in fact, you might see a block here that I've already asked for, I've already seen before in the cache, so an individual day might actually get decomposed into multiple subqueries. And you have to be really careful here. You have to be really delicate. You have to think about inclusive and exclusive boundaries. And if you're like me, you get it all wrong and let somebody else fix it. Because I got it all wrong, basically. But it kind of worked. And when you're just viewing a squiggly line in the graph, it was fine. And then somebody else came along and said, no, you've got all of the boundaries off, and fixed it all. And that was Brian. He did a great job. I should give him a shout out. He fixed all my bugs. And then we dispatch these queries in parallel. We actually add another step because, as I touched on at the beginning, Cortex is a multi-tenant system. So we run a single big cluster. Well, actually, we run about 4 or 5, but we run effectively a single big cluster and have hundreds of users on a single cluster, all with partitioned off data. And one of the things we really wanted to avoid is one user coming along with a really, really big query and killing all the other users. And so these actually get queued, and then there's a scheduler, which is really, really simple. It just randomly picks a queue. But it means that at least we have some really basic quality of service between users. If a user comes and mashes refresh, does 100 QPS in the queries, everyone gets slow evenly, and that user who's doing 100 QPS will starve themselves. But you don't need to know that. So, but wait, one more thing. Right now I've talked about Cortex and how we've made Cortex faster and Cortex this and Cortex that. It occurred to me, I think actually after talking to Bartek, it occurred to me nothing here is Cortex specific. This is just a PromQL caching library process. It just implements the PromQL API at the front and talks to things that implement the PromQL API at the bottom. So we can make this work for everything. We can make it work for Thanos. We can make it work for Prometheus. We can make it work for anything that's implementing the PromQL API, which one of the things I love about the Prometheus project is more and more things seem to implement our API and our query language, which is so cool. So yeah, this PR got merged yesterday. Conference-driven development, and you can now run this against any Prometheus API-compatible thing, and it will do all of the stuff I've just talked about, and that's what I'm going to give you a demo of. Can I ask you to hold my... Thank you, please. Pleasure. So, one of the things I mentioned as an answer to a previous question was about robust perception, which is Brian Brazil, one of the other Prometheus maintainers, startups. And they run a publicly accessible Prometheus instance, which is fun. It's at this URL here, so let's just copy that. So one of the cool things about this is, to do this demo, you need a Prometheus with like a few days worth of data in it. And I don't have that, because, I have a laptop. So one of the things I wanted to do was find a service that did, and I just used Brian's. So this is a histogram query, and I use histogram because they tend to be expensive. And I'm just going to see what Prometheus's latency is. 50th percentile, so it's median latency. Yeah, I did actually paste that in there. Let's make this a bit bigger. Okay, so you see that's quick, right? So this is going to be a rubbish demo if the Prometheus is that quick. So what I'm going to do is I'm going to go to the graph. So it's now getting a bit slow. It's 100 milliseconds, and I'm going to say, I really don't like this server. So just keep going. Keep going. Right, we've done a 1-week query. It took 1.2 seconds, which was a bit quick. 1.2 seconds, a bit quicker than I like. But let's just hope it's slower for the rest of the demo. So now I'm going to go to, this is not my laptop. I've had to install my demo on Dom's laptop. No, it's not Dom's. Is it yours? It is Dom's. Okay. So this is a Grafana instance. Everyone should be familiar with that. I'm going to add a data source. We've already got a data source. I'm just going to rename this one to be with caching. So we know. Nope. Good. It's because I need to run this. So I've downloaded. Somebody's deleted it. This is okay. It's up here. This is Z shell. I have no idea how Z shell. So I've downloaded Cortex. This is just straight off the master branch this morning, this afternoon. I've compiled it, which on this laptop took about 5 minutes, which is embarrassing. And I've run it, and we've shipped Cortex now with a YAML file to configure it to automatically set it up to do all of this. So you don't have to worry. Configuring Cortex in the past has been pretty tricky. Now it's super easy. So you see, we're running a Cortex. It's serving on port 9091, and it's talking to robust perception. Good. So if we test this, it's now working. So now I'm going to add another data source, which is just the robust perception one. And I can't remember or type. I don't really write code anymore. So I'm just going to copy and paste, because that's how people write code nowadays. So that works. So one of the things we did in Grafana 6 is we released this thing we call Explore, which is just us doing the Prometheus query editors just straight in Grafana. And you can type queries into it, and it does them. And it also does tab completion. I don't know why I'm telling you this. It's got nothing to do with the talk, but I just think it's cool. So where's that query gone? I'm not going to try and type it. We've discovered how difficult that is. So if I run this query, last 6 hours, you see it says here 0.4 seconds. Yeah? That was the last 6 hours. So let's just make that bigger. What did we say, last 7 days? There we go. So how long did that take? 4 seconds. Okay, so this is straight to Brian's Prometheus. If Brian's watching, please don't turn it off. So now what we're going to do, we've just started the Cortex front end, and so it's not got anything in its cache. So we're just going to send it to the Cortex front end. What this is going to do is execute the query in parallel. So it should execute 7 queries against Brian's front end. We see if it's any faster. And it took 1.6 seconds. Yes. So this is just showing that executing, thank you. This is just showing that executing queries in parallel against a single Prometheus process can be faster. And actually, Gotham and we were talking about this earlier in the week, or yesterday, and he was like, no, it'll be the same. Because Prometheus has got like a semaphore in it to stop too many parallel executions. But luckily, this is faster. But now the really cool thing, if we run the query again, it should hit the cache, and the cache is on my machine. And it'll only go back to the Prometheus server for the bit over here that no one's looking at to make sure it gets live data. So let's see, if we hit it again, there we go. It was so fast, it took 300 milliseconds. I'm so happy that worked. Right then. I literally did that demo, set that up yesterday morning. So I'm so pleased that worked. So what does the future hold? We wrote this design doc quite a while ago now, when we were actually doing a lot of this work. No, I don't want to sign in. Okay. Well, you can read the design doc yourselves. The slides will be off my Twitter account after this. So I wrote this design doc, and parallelizing the queries by time is super cool, right, and makes it faster. But what I really want to do is parallelize the queries by series as well. So you can think of time in one dimension, series in the other dimension. I want to split each of those days, I want to split into 100 different shards, each that consider 1/100th of the series. But you can't just do that automatically. You have to parse the PromQL expression. You have to look at different subtrees that are doing aggregations. And so I've got I really wanted to demo this, and I submitted this talk to PromCon, and it didn't get accepted because Bartek and I are giving a talk instead. But I really wanted to I really wanted to demo that because it's super cool, but I haven't written the code yet, or I've written very little bits of it, so not ready yet. So something that Ganesh, one of the other Prometheus developers on my team, did was make it so that we can automatically identify subqueries within the expression and automatically replace them with relevant recording rules. which is super cool. We've not merged it. We haven't really finished that development, but this is a nice idea where if you've already pre-computed an aggregate, we could sub it in and go, hey, there you go. And then I've been talking to Bartek about maybe embedding this in Thanos. And actually, Bartek refactored this code base to make it easier to do that a few months ago now. So, maybe that'll happen, we'll see. And then now we're starting to overlap a bit with stuff that Thanos does, right? Because one of the things we've noticed is we run this internally in front of our Prometheus pairs. And we also run Cortex, and most of our query load goes to Cortex. But as we, develop on Cortex and break it, sometimes we have to fall back to asking our Prometheuses why we broke Cortex. And so it'd be super useful if this library would handle gaps in HA pairs. So it's something we're thinking about. And yeah, what do you all want to see? Is this useful? Is this easy to deploy? Does this make things faster for you? Is it reliable enough? Do you spot any bugs? What do you want to see? That's it for me. Thank you very much. Who has a question? Go on then.
What do you use as a lookup value into the memcache? Do you just take the raw query itself, or do you do something funkier?
No, that's a really good question, actually. So we have to include, the key is a composite key. We have to include the day. The key can't contain the query, because the queries are arbitrary length and memcache keys are limited in length. So we actually hash the query. You have to include the step value, because if you ask the same query at two different step values, it's two different queries. And I think that's it. But then because we're using the hash as the key, the hash of the query, there's a chance for collisions. So we then, inside the memcache is a snappy encoded protobuf that includes the actual query you asked that then gets double checked.
So how do you invalidate your cache?
As question was, so I should be repeating them. The first question that I've already answered was what's the cache key? The second question, which is how do I invalidate the cache, is I restart my memcaches. The whole idea is that this is perfect. And so, seriously, you can't write old data to Prometheus, right? You can't write data to Prometheus full stop, right? So once the data's hit the cache, it's immutable. And now, unless we've got bugs in our implementation, which, there's definitely been some, you shouldn't have to invalidate a cache. Now I know we actually have some bugs and do occasionally have to wipe the caches away. And so one of the things we've been thinking about doing is putting some control over invalidation in, but we haven't needed it yet, really.
What about delete series?
So the question was, what about delete series? Don't delete series.
GDPR, I know.
Yeah, so in that case, we just invalidate all our caches. We just restart the memcaches. That's what we've done in the past. More fine-grained control over that. Do bear in mind, these caches are there as an optimization. You can just throw them away and restart them, which is kind of nice. So the question, what about GDPR and deleting series? On then.
So when your day cuts in half because of a partial resolve and filling other partial resolve for a single day, do you have any strategy are you thinking about ever cleaning that cache up to replace maybe two chunks with one chunk?
Yeah, so the question was, when you have a day that's half split, like today is in America, what do we do? Do we have multiple entries in the cache? We actually only have a single entry because the entry in the cache is defined by the day, the query hash, and the step. So what happens is there's actually a read, modify, write in the cache. So we read from the cache, notice that we've got some more data to put into it. The cache, the proto contains a set of what we call extents, which is just a name for the data structure. And we do have an algorithm which merges extents, but it's we don't actually ever end up with multiple entries in the cache for the same day. That merging happens. And of course, if you ask, it's read, modify, write, it's memcache, there's no atomicity. So we do, if you ask the same query twice, they'll clobber each other in the cache, but it turns out it doesn't matter. One more question. I know Bartek's got a question.
Yeah,
What's your question, Bartek?
You sure? Maybe someone else?
Does anyone else have a question? No one else is putting there. Because he asked me it earlier.
Anyway, my question is, so you said that there's possibility to put this as a library to Thanos, but why would you do this if you can put this Cortex layer on top of Thanos? Because
That wasn't the question you asked me earlier. The question you asked me earlier was, how do we compare to Trickster?
that's another one.
Okay, so what was your question was why would we embed this in Thanos if we can put this as a process on top of Thanos? I think it's a really good question. When we discussed embedding it, this didn't exist. So that's one reason. I would also argue, and one thing I learned from Thanos, one of the reasons we've gone to a much simpler architecture for Cortex is people who don't run on Kubernetes, which exist, they don't like deploying multiple binaries. So it's hard to deploy lots and lots of binaries on just a vanilla Linux box. I know Kubernetes optimizes for this and makes it super easy to just run one more thing, but not all people use Kubernetes. No, despite what we'd like, not all people use Kubernetes. So therefore,
Some use Mesos.
really? Don't you mean D2IQ? Sorry.
So what about the Trickster then?
So, oh yeah, that's a good question. What about Trickster? How do we compare to Trickster? That's an interesting question. So, funny you should mention. How do we compare to Trickster? So we've already covered the reusability bit. We put a lot of effort, like the architecture when we built this was a set of what we call middlewares, which are like higher order request handlers. Like you can pass one middleware to another middleware and they wrap and this kind of stuff. It's just a software architecture point. But this makes it really usable as a library. That's the whole idea, or trying to make it more usable as a library. We chose Memcache instead of Redis or Redis that Trickster uses, and I think Trickster also has the ability to have a persistent cache using RocksDB. Something, I don't know. We don't have that option, and we use Memcache instead of Redis. I don't want to get into that flame war, but Memcache is better than Redis. Any Redis fans here? No? Okay, you all agree. Great. Oh, one. Okay. Yeah, no, I don't know. I just chose Memcache because I wanted a cache and it's got it in the name. We're multi-tenant. I don't believe Trickster's multi-tenant, although I don't know that for a fact. We split by day and execute in parallel, and now I thought Trickster did that already, but Gotham combed through the code base and says, no, they don't. So yes, we can say we do that, and we do. And we have this QoS queuing scheduling thing, which is only really relevant if you run on Cortex. Like, it's not really, in fact, literally, we turn it off when you run it on top of Prometheus. But maybe we find a way of doing that on top of Prometheus in the future, I don't know. What we're missing, so Trickster has this idea of doing fast forward. And this is kind of cool, actually. I only realized they did this when I went back and tried to write this slide. This is the idea. They do that step alignment like we do. But because that step alignment might miss the last 10, 15 seconds of data, because you're aligning back, they add another data point in, which gives you that trailing edge. And so it's going to, move around a bit on your graph, but at least you're going to have the most up-to-date data. Now, if you're on a 15-second scrape, that's probably not important, or a 15-second step, rather, that's probably not important. But when you do really, really long queries, and your step is hours or even days, suddenly I think that's actually quite a nice feature. So Trickster does that, and I'm sure we'll end up doing it soon. Gotham asked me to put this one in, if he's listening. Hello. I'll be asleep now. Trickster is more widely used, except for none of you here use it. So who uses Cortex here? Yes, Cortex is more widely used. And that is me. Thank you very much.